inside of the HAL, they included this as the random number generator function. So now you have a, what might have been a decent design in Norway, getting poorly documented in Germany, and then copied by a software developer in Texas as an example to be copied by everyone on Earth trying to write an operating system for this chip in minimal time. When I showed you the pink children's toy, I wrote the operating system for that in one evening. And you can bet that I didn't double check the random number generator until later. So all of the example software for this, from the hardware extraction library, which still has not been patched, all the way up to their reference implementation of ZigBee, which they give away for anyone trying to generate a ZigBee device using their chip, contains this same vulnerability. And it gets copied at each stage. The ZigBee stack designer copied it from the HAL library designer, who copied it from the data sheet, who copied it from an internal memo somewhere. And at each stage, it just gets deeper into these products. And if you change the data sheet now, the product has already been designed and shipped. The library has already been designed and shipped to product developers. And it's been copied in between. The version control internally with these sorts of firms is just now going over to revision control systems instead of emailing zip files. The bootloader that I showed you a picture of earlier, it was done by the copied zip file method, and you can actually see where vulnerabilities were fixed and then reintroduced as they needed to recover the space or as files got shuffled up. So they finally fixed this in February of 2010 for their ZigBee stack, not in their documentation and not in the HAL library or any of the other examples. The way that this infects the Certicom library, because remember, Certicom claims a patent on the cryptography used by this, and they demand that it be in a separate module, which gets statically linked in only after it has been purchased separately with the NDAs and paperwork and stuff. So they call this the ZigBee security engine, and every chip vendor has their own name for this. So Ember calls it something else, and I'm not sure what Freescale calls it. It takes pointers to the key pairs. And then it also takes a getRandom function. And it uses this to generate the ephemeral key. So this third parameter here, ZCL general key establishment getRandom. All this does is grab bytes from the bad pseudo-random number generator. The exploit sequence is that Mallory authenticates with Alice. Alice provides her public keys. Mallory provides chosen keys. So Mallory can make up any static and any ephemeral key pair she likes. It does not have to be signed. And she can choose this to expose whatever information she wants of Alice's keys. She then looks up Alice's ephemeral private key in her 20 megabyte SQLite database. And then she calculates Alice's static private key using Leadbitter's technique. And she can now impersonate Alice. So during any other ECQMV exchange, she can present Alice's public key, knowing Alice's private key. And because the public key is signed by the certificate authority, everything works out. And note that her private static key is exposed. So, I mean, this is her identification. And Mallory does not need a valid certificate to begin with. They aren't terribly hard to get, though. If you want one, you just erase the flash of the chip, dump RAM, and search it. There's a single C struct, which contains the key pair, and it's always the same distance from the certificate authority cert. And that bug still hasn't been fixed a year and a half after it was reported in the example libraries. Some of the individual vendors have fixed that, though, so, but not the examples. In any case, patching this is really hard. It's a common thing in IT security lectures, especially the introductory ones, to say like, you've got to keep your system up to date and patched and roll things out and all of this other gung-ho crap. In embedded systems, you as the customer do not have the option. If I have a network of 10,000 electric meters that have this vulnerability or any other, I have to go to my device vendor and I have to say, hey, look, I think you might have this problem. Talk to your vendor to get a fixed version of the library. Because everything is statically linked and copied and pasted from examples, you can't update a single library as you would on a PC. Instead, there is a single application running. In many cases, you don't even have preemptive multitasking. The best you'll have is a single interrupt firing. And to patch this without your immediate vendor's cooperation requires that you dump the firmware, disassemble it, patch it, and reload it. And if the JTAG fuse is blown and there's no bootloader or remote update mechanism, then there's no way to replace the software, even if the vendor is willing to write you new software. So then you find yourself in the position of having to live with the problem or replace 100,000 devices. And if the warranty only covers a single replacement, you might wait a decade to do that. A good random number generator isn't that hard to build. You just throw analog measurements into a SHA-1 hash, and you keep it spinning for a while. Or you can use the hardware AES implementation of the chip to do the same thing. And then in this case, the computation is actually hardware accelerated. And because you're doing this during the key exchange, you don't need the AES unit for anything else. And the hardware entropy sources exist everywhere in these chips. You just create a little bit of noise on an analog input pin, and you have everything you'll need. You can also use the analog noise that comes in through the radio. So you just listen to static and feed that in. Don't listen to the signal strength of static. That's coming up in another lecture. So this was patched in February. The applications using it also have to be patched separately by the vendor that built them, and everything on the network has to be patched. So not only your meter, but also your thermostat, your refrigerator, your washer, your dryer, your everything that's connected to the ZigBee network you wish to defend. And the cold boot vulnerability remains. I can connect, erase the chip, dump the RAM, and grab the key from everything written remotely like the example firmware. Dealing with competitors, Ember ZNet Pro. Ember was a software development company that later went into hardware design. Their first generation of hardware chips sucked. The second generation is quite good. When I released the random number generator vulnerability, I got an email from Ember within a day saying that they'd checked their code and they were not similarly vulnerable. I'd already checked their code with ARM's OBJ dump, and they were correct. The deal is that it grabs a couple of random numbers from the radio, and then it feeds that into an AES 128 loop. And it reseeds every now and then to ensure that the pool remains proper. The Certicom library is a problem because if it has a timing attack, everybody has a timing attack and everyone has the same timing attack. And I have 5 minutes, so I'm going to race the next 3 slides. Certicom could have fixed this problem if Texas Instruments did not, but doing so would have made the library larger. Perhaps if they had implemented a testing mode, which would just ensure that the random numbers were not crap, that could be swapped out for deployment, this would fix things. The other problem is that because it requires an NDA, a no-compete agreement, and a credit check, and anyone writing a competing library is actively threatened with lawsuits for patent violation, a lot of vendors won't implement the crypto library. They won't ship it. And if anyone on the network is not using it, then you've got to downgrade a bit. Microchip's SSL stack is used in the Google Powermeter, which is not a ZigBee device. The Google Powermeter device is actually a web API. So if you're in web hacking and you want to start playing with power meters, you'll be able to do that very soon. Their reference implementation uses the Microchip SSL stack, which uses a SHA-1 pseudo-random number generator. At first I thought this was exploitable, but now I'm convinced that it's not. It's seeded by a 1-byte timer and a 1-byte MAC address. And this is done on every packet reception. So the entropy begins very small, but it grows quickly.